Hi guys, welcome to Science Chomp. Today we're going to be looking at the laws of thermodynamics. There's 4 laws to worry about, and the first one is, as I've written here, the 0th law. Now the 0th law states that objects in contact are in thermal equilibrium if they have the same temperature. Nothing else matters. So when it says nothing else matters, the material doesn't matter, the size of the object doesn't matter, nothing matters. Basically, if you've got one object here and another object touching it and they're in thermal equilibrium, that means that they are both at the same temperature. Dead easy. This leads to the first law of thermodynamics, and it states that the change in a system's thermal energy is equal to the heat added to the system minus the work done by the system. We can actually express this as follows as well with an equation. So change in thermal energy, we call that delta E. Sometimes people use delta U. That can also be used, but delta E and delta U are used interchangeably. Technically, delta E is the change in the total thermal energy, whereas delta U is the internal energy to do with the molecules of the gas. They're basically the same thing. There's a very slight difference, but it doesn't matter. We use delta E here, and it's the heat minus the work. So the heat is the heat energy put in, measured in joules, and that's Q, and it's minus W. Now, we need to be extremely clear about this bit over here, because I've seen people put Q plus W. This is the first law, it's Q minus W, but it comes down to interpretation of work done by the system and work done on the system. So let's figure that out. Let's consider these two things here. So this is a piston, these are pistons, this one's getting bigger and this one's getting smaller over here. Now there's 2 things that we must consider. First of all, what's the work done by the system and what's the work done on the system. So by the system and on the system. Now from the point of view of the gas would be basically the system. The work done, since it's pushing something, is pressure multiplied by delta V. However, in terms of work done on the system, that would be work equals minus P times delta V. It's basically a different way of looking at it. Now, let me put it the other way. It might make sense if I look at the compression version. Now, if you're doing work on this system, if you physically did work, what you'd do is you'd push that piston down and it will have this situation over here. Now, when you look at it that way, it's obvious. Work done by you is equal to P times delta V. However, from the point of view of the gas, the system, it's the opposite. Basically, this is being pushed in, so that's doing negative work. So for the system, so work done by the system is work equals minus P times delta V. So it all depends on your perspective, whether you're the system, you're doing work done and you are the system, or you're doing the work onto the system itself. It's kind of a little bit confusing, but just bear with me with that particular one. So going back to the laws of thermodynamics, the first law is Q minus W. Again, I've seen some people put plus here, and it all comes down to your perspective of whether the work is done by the system or on the system. But we're looking at by the system here. So the change in thermal energy is the heat minus the work. This is also called the law of conservation of energy. Energy is never created or destroyed. It just gets converted from one form into another. This leads to the second law of thermodynamics that states that When objects of different temperatures are brought into contact, the flow of thermal energy is always from the higher temperature to the lower temperature. Now, what does that mean? That means if I have a hot object over here, and it's next to a cold object over here, you're going to have a situation, and suppose that's like 80 degrees and this is like 30 degrees. The heat is basically going to travel in this direction, and then after a certain amount of time, it's going to reach thermal equilibrium where this hot object gets colder and this cold object gets hotter, and it equalizes to the same temperature. This leads us to the third law of thermodynamics, which states that it is impossible to lower the temperature of an object all the way down to absolute zero. Now, you may be wondering, why is this? Well, it all comes down to how you have to cool an object down. So suppose you got an object over here. Let's draw it in red, like so. And it's got a little bit of warmth, but it's fairly cold. Well, in order to cool it down to absolute zero, you've got to surround it by other cold things which are at absolute zero, which is, by the way, an impossibility. And what's got to happen is the heat from here needs to get absorbed by all of those. Now, as a result, what happens is this thing can get close to absolute zero. That's 0 Kelvin. However, what's going to happen is this is going to absorb some heat. This is going to absorb some heat. This and this going to absorb some heat. And eventually it reaches a thermal equilibrium a tiny, tiny little bit above absolute zero, which is 0 Kelvin. For that reason, you cannot get something cooled down to absolute zero. So that's it. That's the laws of thermodynamics. Just one last little thing. You may be wondering why it goes 0, 1, 2, 3 and not 1, 2, 3, 4. Well, the reason for that is the first law and the second law, they were discovered in 1850. Followed by the 0th law, and they figured the 0th law was a little bit more sort of basic than the first law, and that was discovered in 1871, and the third law was discovered between 1906 to 1912. And so for this reason they went 1, 2 and then 0 and then 3. There are more videos on thermodynamics coming because it's quite a complicated topic. So look out for parts 2, 3 and 4 coming up soon. Thank you very much for watching. Like, share, subscribe and donate if you can. Thank you. Goodbye.